Hi, my name is Ted Cross, and I'm a technical advisor with Novi Labs. Today I'll be presenting our paper, Are Unconventional Well Performance Gains Exhausted? Investigating the drivers of year-over-year production improvements across the major U.S. unconventional plays using machine learning. I'd like to thank my co-authors, John Chaplin, Kieran Sate, and Alex Tway, for their contributions. Everyone listening to this presentation is probably aware that unconventional oil and gas wells have seen tremendous performance gains over the past decade, reshaping our industry. To put it into context, we've gone from being a 6 million barrel a day producer to over 10, becoming the top producer in the world. People have gone out and written entire studies about the impact of these unconventionals on the domestic economy and various industries, and even Foreign Affairs has covered the geopolitical consequences of the shale revolution. For each of the main plays, oil plays, here we're looking at Bakken, Delaware, Eagle Ford, and Midland. Oil production has more than doubled on average, looking at 1 year cums, going from stuff down in the 80s or 90,000 barrels to kind of up into the 160, 170 plus. However, production has plateaued starting in 2016 or 2017, with some small gains still occurring in the basins, but nothing like the dramatic performance improvements that we're seeing from 2014 to 2017. Understanding what this might look like in the future as the shale industry goes deeper into the 2020s requires in part understanding what actually drove the tremendous performance gains of the previous decade. So in this paper, we study the relative impact of what's thought to be the main levers of this dramatic increase in performance, that is upsized completions, longer laterals, and increased focus on higher quality rock or sweet spotting across these four key oil basins. We trained 4 different models across these plays. We had the Bakken Three Forks of the Williston of North Dakota, the Wolfbone of the Delaware, the Wolfberry of the Midland Basin, and then the Eagle Ford in the Texas Gulf Coast Basin. For input variables, we had for completions, proppant and fluid volumes, total volumes, we normalized those by length. We also had stage counts available for the Bakken. We used lateral length available from, in some cases, the regulator, or also from directional surveys if we didn't have it from any other source. Spacing, we calculated drilling densities in terms of wells per section. Timing, parent-child relationships. Geology, we had some interpreted subsurface grids. We did remove standalone parent wells from our analysis as they can kind of skew the results. And then we also excluded wells with less than 200 pounds per foot proppant. So that just improves the modeling results, as those wells from those kind of pump and pray days are not super relevant today and can kind of mess up the models. We did not include operator, latitude, longitude, county, or area. Clusters was not available publicly. Fluid type, we generally do not use in our public data models just because it has overall kind of low quality and total fluid does a pretty good job of capturing the impact there. And then post-drill operational decisions, like lift type, choke management, that those types of data are usually not available publicly, and if so, are not in great shape. So we trained separate models for each basin, each of these four basins that we were looking at. We used a decision tree-based modeling approach, extremely random trees, which is similar to random forests. Basically, it creates an ensemble model of decision trees to create a robust model and avoid overfitting. On the right, I have a schematic tree, just a cartoon to kind of show you roughly how this works. The model will start with a set of wells for training within a given basin. It'll then attempt to split them according to certain parameters, like let's say water saturation, depth, completions. And it'll do a series of these splits. Eventually, its goal is to group these into different groups of similar wells that have different ranges of production. So at the beginning, we had 90,000 barrels on average. And at the end, we have different groups of wells that have a much wider range of average 1 year cumulative values. So the model is essentially learning how to group and split these. In some ways, this is similar to an analog type curve approach, just on a computerized speed. For our models, we predict a 36-point vector of monthly cumulative production going from day 30 to day 1080. So essentially, the first 3-year production curve. We're going to spend a lot of time today looking at SHAP values, which are what we actually use to answer the question of how these different variables actually impacted the performance of the wells. And these are named after a mathematician named Lloyd Shapley, who was attempting to answer the question, if a bunch of people work on a group project together, how much credit should each one get? He went on to win an economics Nobel Prize, and I had this great quote, "I consider myself a mathematician in the orders for economics. I never in my life took a course in economics." So nice sense of humor, that guy. But his work was rediscovered recently by the machine learning community to, rather than credit an individual on a team project, to credit a training feature or variable on a model prediction. So this impact of the feature is known as a SHAP value. So it's short for Shapley additive prediction. So for us, a SHAP value is in units of barrels and represents how much the feature impacted the prediction in a positive or a negative way. All of these are compared to the average training well, so it's not purely in the absolute sense. It's kind of compared to the average, so it'll be plus or minus compared to average. And we convert these to a percentage to normalize basin to basin, which just makes for ease of comparison. So here what I'm showing you is a waterfall chart of SHAP values for a single Delaware well that we've taken as an example. On this chart on the right, you see on the x-axis we have variables, proppant fluid, lateral length, parent distance, wells per section, TOC clay volume, thickness, and depth. And each of those has a red bar if it has a negative impact, and the green bar if it has a positive impact. So for this well, it has less proppant than average, and so it's getting a negative impact from the proppant. Fluid is very small impact, probably right around average. Lateral length is getting a nice bump, so it was probably a longer well. We see some of the other variables like wells per section, parent distance, so it was probably like nice and far away from the parent, relatively widely spaced. Nice TOC values, nice thickness, but maybe it's relatively shallow and low pressure. So when you add up all these different SHAP values, we get this bar over here on the far right. That's approximately plus 20%. So that would be telling you that for this well, the variables combined to push the oil forecast 20% above the average for the training Delaware wells. So this is what we get on a well-by-well basis. This is kind of the raw data set that we start with. So what we then did was group these different variables that you see here into categories. So we have the geology, we have the completions, etc. So when we display those groups through time, it'll show the aggregate impact of the variable through time for each basin. So that's what we'll be looking at for the rest of the presentation today. So we're going to start with the kind of key conclusion slide right here, and then we'll go through each of the different components, spend a little bit more time with it, and think about what the implications are. But what we have over here on the right is, like I've said, we've taken those SHAP values, we've binned them together according to each of the different categories, and then showed the average through time for each basin. So on the x-axis, we have the quarter when the well was fracked. On the y-axis, we have the sum of the SHAP values for that category. And each of those bars is colored by the category. So we have completions, geology, lateral length here. In blue, completions, yellow is geology, green is lateral length. So just kind of a high-level view, some stuff that we can see just from this bird's eye level. First, the SHAP values match what we were seeing in the average production trends, which is as expected because the model is learning how to predict those wells and how to forecast them. So it should match, and we're looking good there. We see that lateral length is having a huge impact in the Delaware, pretty big impact in the Midland. That's in the green there. Geology is having the biggest impact by far in the Midland Basin. And then completions is significant in each play. So we're going to spend some time going through each of those here in a little bit more detail in a second. But first I wanted to show you kind of breaking those out by category across each basin just to see kind of how the timing looks of this. So if you remember from the very top, we had that change, that kind of inflection point was hit in 2016 or 2017 when these wells went from being, that nice upward, convex upward trend of performance improvement. They kind of plateaued or even totally flattened at that point. And we see that actually the completions for the Bakken, Eagle Ford, Delaware, and Midland all plateau at that same point in time. So that's matching what we saw in the average production. For the geology, you can read this as the change in the average quality of rock drilled within a basin through time. So this is really just trying to, were they drilling mostly tier 2 rock, tier 3 rock, tier 1 rock, and how did that vary through time? And, for each basin, there's a slight increase at a minimum, Bakken, Delaware, and Eagle Ford through time, roughly, again, plateauing at around 2016. For the Midland, we see by far the biggest change. So we'll spend a little bit more time on that in a bit. And then for lateral length, we see that across each play, that actually continues to increase through the edge of the data here in 2020. So compared to the other ones, that one is still seeing the largest increase out there at the tail end of our study. So now we'll step through some individual variables here, and we're going to start with the proppant intensity. Proppant intensity, this is often held as the most important completions variable, at least in the literature and a lot of common discussion that you'll hear. On the right, what we're showing you in that light blue is the average proppant pounds per foot for each of these different plays. Delaware having the highest, kind of peaking at 2,600 pounds per foot there in 2017. In the Bakken, we're peaking, late 2016, early 2017, but at more like 1,400 pounds per foot. Eagle Ford around 2,500. Midland on average 2,200 or so. For each of these, again, we see that kind of plateau starting at 2016 there. And in the green bars that you see behind are the impact of that proppant loading on the model forecast. So basically just what we were seeing on the previous slide in terms of how that's changing through time. But we're seeing pretty good agreement in terms of the proppant intensity and the completions impact, which is to be expected. The other completions variable that we have for each of the plays is fluid intensity. This one is publicly available, just like proppant intensity. Maybe a proxy for fluid type, where the larger fluids more likely to be slickwater jobs compared to the smaller fluid intensities. And same story as what we saw for the proppant intensity. It's kind of plateauing in 2016, 2017. We do see that in the Bakken, we're actually having the largest contribution, even though the total magnitude of the fluid loading is a little lower, which is pretty interesting. Could be something related to the geomechanics or the permeabilities there of the rock. We do have another talk that goes into more detail about the impact of fluid, so check that one out if you want to get some more detail on that. But generally, we're seeing very similar trends between the fluid intensity and the proppant intensity and their impact on the performance through time. For lateral length, this one is super interesting because, unlike completions, we are seeing that it's continuing to have a positive impact, but it's very different across the basin. So if we look at the Delaware, in orange there, we see average lateral lengths increasing from 4,000 feet or so up to, nearly 8,000. In 2019, early 2020, whereas the Bakken's been chugging along there at 8,500, 9,000 feet on average, really since the end of 2011. You see that big increase in green bars and chap values for the lateral lengths in the Delaware is we're not seeing that in the Bakken, and that's not because lateral lengths are not efficient in the Bakken. It's just because they haven't really seen a big amount of change. And in the Bakken, you have, at least in North Dakota, you have forced pooling on 640 acre or 1280 acre units that really promotes, at least from a regulatory perspective, the drilling of 10,000 foot laterals. You also have favorable geology compared to some of the other plays. We also see that the Eagle Ford has by far the lowest lateral lengths out of all of these plays, It was developed earlier than the Permian, so subject to that same Texas regulatory regime, but without the kind of, with that Texas regulatory regime and drilling earlier, that means you're kind of locked into shorter units than you are in some of the other plays within Texas, that is. The other thing is within the Permian, of course, you have much greater share of HBP or held by production acreage compared to the Eagle Ford. So that probably allowed operators, they didn't have to go drill a bunch of parent wells to lock in the acreage. So they were able to kind of slowly piece together longer and longer units, which is definitely paying dividends in terms of the production that we're seeing on an average basis in these plays. So geology, if you remember, this is the chart that I showed you before. The Midland Basin, we see by far the biggest swing in average rock quality through time. Definitely like much greater magnitude compared to the other plays. So if we actually look at where wells were drilled in the Midland through time, I have 2013 and 2019. On the y-axis, I have the county. We see that in 2013 is mostly Reagan, Erie, and Crockett counties. Those were the top three in the Midland. Totally different set here in 2019. We have Midland, Martin, and Howard counties. Those are in the northwest versus the southeast part of the play. Definitely looks like operators, like in the gross sense, shifted their activity from the southeastern part of the basin to the northwest. That scale of a shift in activity to the basin sweet spot isn't really observed in the other basins. I mean, we do see some improvement in where operators are focusing their drilling as the plays are delineated, but here, for example, we have the Bakken, really kind of the same share, McKenzie, Montreal, Williams, and Dunn being drilled in 2013, 2019. Some of the fringe plays, fringe counties not being drilled quite as much here in 2019, but on the whole, a much more similar set. I'm not exactly sure why this is the case. I have had some people familiar with the basin tell me that basically for whatever reason, drilling just started in the southeastern part of the basin, and then just because operators can be more fast followers, there's just a lot of activity down there until it was really kind of discovered that wasn't the most productive part of the basin. I'd love to hear your comments. Feel free to shoot me an email or a LinkedIn message on why you think we're seeing that huge time variant rock quality drilled within the Midland. So to conclude, based on what we've shown you today, we see completions and rock quality's contribution to well performance plateauing starting in 2016, 2017 across all four plays analyzed. And this matches the slowdown in the average well performance. This suggests that the upsizing of completions and the direction of activity towards higher quality rock have hit their productive limit or economic limit, at least in these plays. Lateral length has continued to make positive contributions since 2017. It's kind of the remaining bright spot that we see there. While there may be remaining potential to continue to improve for well performance, 12,000 foot laterals, 15,000 foot laterals, this should have a negative or negligible impact on production in aggregate on the operator or the basin level. And that's just because two 7,500 foot laterals versus one 15,000 foot lateral, you're still producing the same volume of rock, plus or minus a little bit of unit line well here or there. And you may actually have some inefficiency. I mean, certainly you have some inefficiency, especially going out there to those super long laterals. So that, economically it might look good, but in terms of, total barrels a day, it might not. I do want to say that while the primary levers of the improved production appear to be mostly played out, the model doesn't know anything about novel technologies. Of course, it's impossible to predict, what our industry might be cooking up in terms of new ways to improve performance. But in terms of what looks like the big impactful design choices of upsized completions, longer laterals, and geologic sweet spotting, looks like those are getting mostly played out. Definitely could see some new stuff start to break that open again, though. And finally, I want to emphasize that everything reported here in this study is averaged across an entire play. Individual operators can still make tremendous gains in their performance. They can optimize for whatever their preferred economic metrics are. They can improve their returns, improve their production, improve their EURs. This is averaging across a lot of mistakes and a lot of successes, and there's still, you might not be doubling your production like 2011 to 2017, but there can still be a lot of meat left on the bone, let's say, for improving returns. Finally, we'd like to thank Wood Mackenzie for providing us the data using the study and for the permission to present it. Thanks everyone for your time listening today. Really appreciate it. And feel free to write me if you have any questions about the work presented here or any thoughts. Thanks.